Hey everyone, I'm Mark Hockman of PC World. I'm here with Dr. Ian Cutress of Tech Potato, and we are here to talk about, well, among other things, Meteor Lake. So Intel sent us to Malaysia as part of its Intel Tech Tour from August 22nd to the August 25th in Penang and Kulim. Full disclosure, I was flown out courtesy of Intel, who paid for my hotel and meals as well. We didn't want to do it this way, but that was the way we were able to get there.
Me too. That tends to be the way they do things. If you don't fly by their dime, they don't let you in.
Exactly, that's right. So Intel has fab operations around the world. Development fabs in Hillsborough, 10nm fabs in Israel, and Intel 4 fab in Ireland. More on that later. And the upcoming Intel 20A fab in Chandler, Arizona. But we also saw the additional part of the process, which is chip assembly, which is putting the dice on the wafer itself. So we're going to talk a little bit about that as well.
Dice from wafer into package.
Into package. Thank you. That's right. So Ian's going to be here to help correct me, make sure I stay on track, make sure I'm accurate, and so forth. But we're just going to go back and forth throughout this whole thing. So Intel had a tech tour last year where they sent reporters to Israel to look at the fabrication operations. This is like chapter 2 of that operation. So we actually, just to give you a little bit of a timeline, we spent a full day with Meteor Lake. We spent 2 days at the so-called Intel Penang Assembly and Test, or PGAT, and the Intel Kulim die sort die prep. So we're going to talk about everything from how Meteor Lake works to how it gets assembled and packaged. It's all very interesting. But the one thing that we aren't going to talk about are going to be some of the questions that you have specifically in mind. Intel talks about new processors in 2 stages. It talks about the architecture first, and then it later gives us all the information that we really want to know, which is speeds, feeds, costs, and the whole works. So we're starting with phase 1 right now.
Well, to be honest, that's all we know.
That's all we know.
That's all we know.
That's right. That's all we know. Exactly. That's right. So we're not going to be able to talk about some of the basic questions. I mean, Intel confirmed to me, and this isn't any great big deal, this is the 14th generation Core chip, but they wouldn't even really answer questions about, say, whether this was just mobile only. This reported Raptor Lake refresh didn't address that at all. So I mean, we know a little bit about this mobile chip, and that's pretty much it. So let's talk about, though, first off, what Meteor Lake is, and let's just hit the high points, and then we'll dive in a little bit deeper. So my reaction to this was very a little bit like Qualcomm Snapdragon messaging. I mean, we're talking about an emphasis on low power. We're emphasis on AI, which is something that Snapdragon chips have had, at least in the mobile space. A leap ahead in graphics performance, and the fourth thing is this disaggregation. We moved to Intel 4, and now we've moved away from sort of this Northbridge, Southbridge model to, I want to say 4 tiles, Ian says 5 tiles. We can talk about that a little bit later. But yes, I mean, we're talking about a disaggregated architecture where all these different functions are separated with a couple of new features. We have low power E-cores now, and we'll talk about those a little bit later. So let's just start here. Ian, what was your top level takeaways from all of this?
It's Intel still needs to do 2 things to its product portfolio that kind of everybody else in this space has. One of them is chiplets on the consumer platform, or tiles, whatever you want to call them.
Right.
And then advanced packaging, right? This does both. And I guess the third one is EUV, the mythical process that actually drives down cost and makes stuff yield higher in the fab. So the fact that Meteor Lake does all 3 all in one go means that this is arguably a big step function in Intel's design and feature process and manufacturing, regardless of where we land on performance. The key takeaway I got from the event is that and the tech day is that they are trying to do a lot. They recognize that the market is changing quite fast. Obviously, some of this stuff had to be put in plan 2 years ago,
of course.
Some prediction is needed. And they're trying to target a market that they think that a lot of these features will be useful. Because I mean, there is something to be said of if you build an all-singing or dancing chip, you don't need it in every device,
No,
right?
absolutely.
And so there's some differentiation here, we think, where it Intel typically does multiple dies depending on the different SKUs.
Right.
That has kind of changed as well a little bit here. And just in terms of strategy, I mean, for the end user, it's still going to be a computer chip. It's still going to run your software. It's still going to run your games. How well it does, we'll find out when they actually get launched and we get some of those details. But to the end user, almost nothing changes. It's just next gen. It's just next gen.
Absolutely. So, I think one of the things that consumers are going to be maybe a little bit concerned about. I talked to Michelle Johnson Holhouse, who is the head of CCG, and she sort of put it.
MJ's amazing, by the way.
Yeah, she really is. And she put it basically saying that. This didn't require any prying. I mean, she was saying that CPU performance is going to about equal Raptor Lake. So, just set expectations. Don't expect some sort of dramatic improvement in performance.
But it's like the TikTok model. It's
right.
You're changing process nodes, not necessarily architecture this time.
Exactly right. 2x the graphics performance is what she said. And then, of course, if we didn't mention earlier, the integrated MPU, so bringing the first iteration of integrated AI into the Intel CPU model. So I think what we decided we were going to do was sort of just talk about this from an individual tile perspective. I mean, it's probably easier to talk with let's start out with the CPU tile first. We've got the new P-cores, Redwood Cove, and we've got the new E-cores, Crestmont, but we also have these low voltage E-cores as well. And let's just talk maybe about those to start out with then, I think, really.
So the CPU tile, again, normally we just talk about the CPUs, but because this is a disaggregated architecture, we just talk about CPU tile. So we have the big P cores, they're technically called Redwood Cove. There's going to be 6 of them in the design. This is going to be paired with 8 low-powered E cores, which are the Crestmont architecture.
Right.
There's a small slight bump in there, gen on gen, of about 8% in terms of IPC.
Yeah,
6 to 8% IPC.
Something
just
like
making
that,
sure our notes align.
No, that's fine. I want to double check that myself, actually.
Yeah.
Go ahead.
And so
4 to 6 is what I have.
4 to 6%. Okay. So we have this sort of 6 plus 8 design. We're going to have hyper-threading on the P cores again, as what we used to. No hyper-threading on the E cores. They're now going to be they are equal in terms of the instruction set they support. That was the same on the desktop parts before, except we don't have this like bulky AVX512 unit that's kind of there but disabled. It's actually a unified architecture design. They're also implementing some additional instructions called VNNI. We've already seen them on the enterprise platforms now, but they're coming to mobile. This is just some like additional acceleration for onboard AI features that are CPU based rather than GPU or NPU based. And that's kind of the CPU tile in a nutshell. This is connected by a die-to-die interconnect to the main SoC tile, and there are going to be 2 additional E-cores on that I/O tile.
Right.
So if we look at
SoC tile.
SoC tile, sorry. There's so many tiles, I can't get my name straight. These 2 E-cores are the same E-cores that are in the CPU tile, right? It's still Crestmont. They're just designed for a lower performance and point and a better efficiency point.
Right.
The idea being that if your laptop is on idle, and mine just went to sleep, so I'm going to have to relog in here. But these are designed for lower voltage, lower frequency, background tasks where you're not in need of immediate feedback.
Right.
That's always been kind of the thing on the ARM ecosystem when it comes to compute. So having these 2 additional E-cores separate from the CPU tile, so you don't need to wake up the CPU tile.
Right, and that's the important bit.
Yeah. That's where a lot of the power savings are going to come in.
Right.
It's the same core between the 2 tiles, but they're actually built on different processes. And as a result, they're going to be configured slightly differently in silicon just to optimize for power and performance. Kind of like if you know about Zen 4 and Zen 4C, AMD made a denser design for Zen 4C because they didn't need to hit the high frequency points. It's that sort of thing here, but for the low power E-cores. Right. And I think, just for clarification, I'm going to call them LPE cores.
It's probably the easiest way to do it.
P-core, E-core, LPE core. So you have 6, 8, 2. And internally, it looks like, based on the tour we had, it's called H682. And we expect there to be a lower core count design coming later, which may have a different H number.
Right.
Exactly what that's going to be, we don't know yet.
And let me just back up this and just put it to sort of restate what Ian said too, because I think it's kind of things that it took me a while to sort of grok as well. So Redwood Cove, I mean, as far as the changes that Intel's talked about, the only thing that I heard was improved performance efficiency and improved bandwidth. There's a larger L2 cache on it, although I'm not sure if they actually disclosed what size it was. And then with Crestmont, again, the IPC gains over Goldmont, I believe it is, are 4 to 6%. And then the low power E-cores are simply a different implementation of Crestmont, is my understanding as well. Yeah. But the key is that, as Ian pointed out, though, is that one of the things they talked about was because of the fact that, the old ways of doing it, monolithic, or even like sort of the North Bridge, South Bridge, where you had like the
PCIe control.
PCIe, PCH, PCH, exactly, with the intermediate stuff. Was that if you touched the logic, you woke it up, and that's the problem. One of the key things for these low power E-cores is the fact that they want to perform these background tasks on these E-cores, and some of the background tasks that you think of as background tasks aren't really background tasks. I mean, they showed decoding tiers. They showed playing back Tears of Steel as a low voltage or low power E-core function. And I mean, we do, and so does everyone else, we do battery life testing on laptops. And when you have a battery life test that touches the main CPU, that's going to be quite a different experience than one that just touches one of those little E-cores, those low power E-cores. It's going to, battery life is going to be a lot longer.
You're simply just not turning on silicon.
That's
you
right.
can totally power gate it. Part of this disaggregated design allows you to have finer control over that power gating. As a result, they had to essentially redesign their power distribution model from the ground up. No easy task by any means. However, they knew they had to do it because they understand that this is now the future of computing.
Exactly.
As we go to more advanced process nodes. I mean, part of the power efficiency gains here is that the CPU tile itself is built on Intel 4. So not Intel 4 nanometer, like you keep wanting to call it.
Yeah, exactly.
But this is Intel's first process node to use the EUV, extreme ultraviolet lithography. So while TSMC has been productizing it for almost 4 generations now, this is Intel's first. So they're going to get a step function benefit in terms of density and efficiency here, which will the density stuff will go unnoticed by most people, but I think the power efficiency here, along with the new power distribution model, along with the tiled model, these are going to be, if not additive, then multiplicative to what people are going to experience in the battery life. It's I've kind of been delaying upgrading until I get one, just to see how it's going to perform.
I don't necessarily think consumers are going to care so much about EUV. Let's just explain it briefly. So EUV stands for extreme ultraviolet.
Extreme ultraviolet. So when you create a computer chip, you essentially shine light through a mask onto a series of chemicals, and either some of them harden or some of them dissolve, and then you wash it away, and then you build up a metal layer. But realistically, you're using a wavelength of light that's larger than the feature you're trying to print on the silicon.
Exactly.
And depending on what wavelength, well, I say light, it's electromagnetic radiation, what wavelength you use determines how fine of a pitch you can make those features. We were on 193 nanometer wavelength light for the last 20 years or so, since the early 1990s. And it wasn't until, I think, 2014, 2015, the first TSMC products came out with this new extreme ultraviolet lithography tool. And we reduced the wavelength of the light down to 13.5 nanometers. There are benefits and negatives to this. the main thing is this was a technology that was first dreamt of 35 years ago. They thought it would only take 15 years to implement, and we had to wait another 20. So there is that. It does mean you're actually using like megawatt lasers to create millijoules of energy to create some of these features.
And a series of mirrors too, right?
Yeah, so efficiency it's one of the least efficient things on the planet to do. But the point is you end up making very efficient chips at the end of it. It helps increase the density, which increases the number of transistors. Increased number of transistors, you can do more things in silicon. So one of the aspects I know I've covered and I know you've covered is this function of different amounts of accelerators on boards to help with, say, video encoding, video decoding, and playback. You have more transistors, you can do more of that as well. Right. So it's of a benefit. However, I'm quite bullish in saying that EUV is kind of like the last major technology in lithography. And that's just due to the physics of it all. EUV, good.
Absolutely. It requires a hard vacuum, too. I thought it was kind of cool, too. Yeah, you can't just do it in air.
It's the systems are really tall. There's only one company that makes them. They're really expensive.
That's right.
I've touched one.
Have you really?
Yeah,
Nice.
I've got a small short on YouTube where I touch one and run away, and somebody runs after me. And the comments on it are blame Ian for the chip shortage.
ASML, is that right?
Yeah, ASML are the company that make the machines, but ASML is essentially a conglomerate of all the big fabs as well.
Sure.
So
yeah, okay, that's fine.
Yeah.
Now, the one thing that I think that's important to mention, though, as far as the EUV, Intel 4, and so forth, is that they did have Bill Grimm, who's the VP of Logic Technology Development, on stage, and one of the things he pointed out, which kind of makes sense, was the fact that if you're producing not just one massive chip, but tiles and packaging them together, the efficiency in doing so is actually improved to the point that they talked about not only is we're talking about power efficiency, which I think the process technology, according to this, gives you 20% better power efficiency, but the yields are better. And that's what really struck me, was the fact that according to Grimm, he says it's going to be the, quote, best yielding product at time zero, which I guess means launch, in more than a decade. So we're going back to 14 nanometer, 10 nanometer, the whole works. That's a big deal.
So one of the benefits therein is, if you imagine the features you're printing on the chip, right? If you're using the old technology, 193 nanometer wave light, in order to make a design feature that's, say, 30 nanometers,
right,
you have to use multiple exposures and the special maths and physics that are involved in that. And each time you do an exposure, that's an opportunity to lose yield. With extreme ultraviolet light, you can replace 4 exposures with 1 because the EUV allows you to be more accurate first time. So when he's saying this is improving yield, it is literally a function of the fact that they require fewer steps to make the product.
Right.
On top of all the different design features that allow for power efficiency. And also creating smaller chiplets. The smaller your chip, the general higher your yield. The number I like to quote is TSMC's N7 process, which is has been widely used for graphics. That process has a defect rate equates to about 45 per wafer, right? So if you make really, really small chips, suddenly you're making 500 chips on a wafer. If only 45 have defects, whereas if you're making massive chips and you've only got 80 chips on a wafer, like a big GPU, and there's 45 defects, well, suddenly you can't use 45 of them.
Right.
Or it's a bit more complicated than that, but...
And just to be clear, Intel's not making everything in Meteor Lake. I mean, it's making its own CPU tile, but as you mentioned before, some of these are being manufactured by TSMC, right? Where the process, the tiles which tiles are being manufactured in which process?
Yeah. So we're all very familiar with the struggles that Intel's had with its manufacturing.
Yeah, absolutely.
The issues it had with 10 nanometer, and then subsequently the renamed 7 nanometer. And now Intel 4 is kind of like the first jump into that EUV market. As a result, in order to remain competitive on the product side, it's had to contract out some of its manufacturing to TSMC. Now, Intel's already been a top 4 customer of TSMC for a decade. So this isn't really new. What's really new here is that actually that silicon is going directly into the CPUs that people buy. So we have this CPU tile that's Intel 4, We have a GPU tile, so latest generation GPU graphics, which is on TSMC N5. Then we have an SoC tile, which is the system on chip. That's on TSMC N6. You have an I/O tile, which is dealing with some of the I/O functions on N6. And so that's the 4 tiles that Intel officially exist.
Right.
There is technically a base tile on top of that, like a passive interposer. That's not given a process name, but it is made on Intel. It's technically called Intel P1227. If you go back like many years through slide decks, you will actually find references to this. But that's part of their advanced packaging, this what they call Foveros die-to-die stacking, which we can get into in a little bit.
Right.
But yeah, so 5 tiles technically, 2 are on Intel, 3 are on TSMC, and the 4 main ones are all using EUV.
And they are, just to make sure I understand correctly too, we have so we have the individual tiles sort of talking to one another. Do we have a new fabric that goes ahead and does that, that replaces the old direct media interface, I guess it is?
Yeah, so previously Intel, when it was a monolithic design, you'd have this thing called the ring bus. And the ring bus would have stations at every CPU core, then a station at the DRAM, a station at the graphics, then a station at all the I/O. And these rings could be sort of like 15, 16, 17 stops long. And there are trade-offs with power and latency when you get to that size and whether they're unidirectional or bidirectional. I think in the previous generation they actually doubled the bandwidth of them by actually doubling the number of rings. This time, because you've got this disaggregated tile structure, you can essentially have like a mini ring inside the CPU tile, and then you can have pathways in the SoC tile, the GPU tile. So it makes it more efficient within a tile. There are some drawbacks to this because it's a tile design. Typically, you like all the electrons to stay inside silicon. With tiles, you kind of have to go from one silicon to another in order to get your communications. There is a power penalty for doing that. I believe, if you're interested, they said 0.3 picojoules per bit, which is really low because on silicon, it's next to 0. But actually, if you look at AMD's solution, it's more like 1 to 2 picojoules per bit. So the fact that it's really low power is really great because it means when you're dealing with bandwidth to the CPUs or the GPUs. But it also allows for a lot of different control in the platform. Especially moving data, especially when you want to wake up. You don't need to wake up a massive ring just to fire up the video decoder, for example, now, because the video decoder's in the SoC tile.
Right, which is actually a great segue because that's what I wanted to talk about next. This SoC tile is honestly, maybe arguably the most interesting tile they have. It's the complex tile because it has both the low power E-cores. This is where the NPU AI engine is located. We've got Wi-Fi 6E and Wi-Fi 7. We can talk about that a little bit later, but that's a hint for you that we're talking about advanced technology. The media controller, DisplayPort, which is actually DisplayPort 2.1 and HDMI 2.1, integrated memory controller, which they didn't actually disclose, but as we asked later, I'm not sure who it was, DDR5 and LPDDR5.
Yeah. It's I'm pretty sure this platform isn't supporting DDR4,
right?
But that's just because new technologies are moving on and such.
So the SoC tile. Let's talk about the 2 things that are probably the most interesting, and let's start out with the NPU because this is, Intel has made a big deal of the fact that this is the first introduction of the AI PC. Pat Gelsinger said a year ago at Intel Innovation that this was going to be this is going to be sort of a big deal. And then they've talked about, this is going to introduce AI to the consumer PC. It's going to be, a foundation for years to come. It's interesting, of course, because to date, AI has pretty much not been a local an issue. It's been something that just lives in the cloud. I mean, everything from Bing Chat to Chat GPT is, you talking to a server. Go ahead, sorry.
Unless you have a smartphone.
Unless you have a smartphone, that's true, yes. And unless you're actually running Stable Diffusion, which runs on your local hardware, which, you can create all sorts of weird cat girls or whatever you want to do. And that's one of the things that, they are talking about is privacy. The fact that eventually you're going to want to have an AI that knows everything that you want to give it, but doesn't talk to anything else. It doesn't exist on a server, so it can't be hacked. So this would be something that could, do your finances or something of that sort.
The way machine learning is being spoken about today, Right, so there are two types of machine learning. You have the training, which
Sure.
is where you need the massive GPUs and the big data,
Mm-hmm.
and then you have the inference. So once you have a trained model, you show it a new picture and it identifies it for you, or you give it a new prompt and it creates a new image for you. The expectation is that the amount of work given to inference workloads is going to be so much more than what training will be in the future. And as a result, there's this desire to move it away from high power in the cloud, or you could say low power in the cloud, high efficiency in the cloud, and you don't spend the extra power sending that data to the device. So how much can you do on the device? That's why we're seeing now not only Intel but also AMD and we know Qualcomm starting to have these AI engines
Right.
or NPUs. Intel actually changed the name from VPU to NPU on our recommendations. Thank you, Intel. And just because NPU has become a staple in the Apple world. Just so everybody understands kind of what it's bringing to the table here. So this NPU, this little piece of silicon, this is actually derived from an architecture acquired by Intel called Movidius.
That's right.
So if you follow the mergers and acquisitions, Movidius happened a few years ago.
2016, sure.
You've got all the dates right there. And they launched a few products under the Movidius brand, and now it's decided that the Movidius architecture has evolved to a point where they can now integrate it into laptop mobile CPU. And more than just simply vision processing, which is why it's called a VPU initially, it can do much more. It can do convolutional neural networks on audio and video. It can do transformers for generative AI purposes. I still think we need to. They haven't disclosed roughly what the performance of this NPU is, but they're working closely with Microsoft to integrate it into the Microsoft, the experiences with the camera that I know you guys, Gordon and Adam, have played with before on the channel. So we get the idea is that we get a unified experience at the Microsoft level between AMD, Intel, and Qualcomm, and then Intel's also opening this up through OpenVINO to do really cool demonstrations and things. We saw a demo at the event called Refusion. This was one of the highlights of the event for me. So what they took a music track. They applied one machine learning model to separate audio vocals from the melody.
Right.
And then they applied Refusion, which took the melody spectrogram as a picture.
Yeah, exactly.
And then applied Stable Diffusion to the picture to change it from one type of music to the other. That process, they put the audio back in, and now suddenly your country music is EDM.
Exactly, that's right, yeah.
With the same vocals,
Right.
Country music into EDM.
It's a little bit different than karaoke.
But my fun thing is it was Stable Diffusion, so it wasn't working on the audio as a wave. It was working on a picture of the spectrogram, and the spectrogram was read back in. Mind-blowingly insane as a model. Great as a demo. I've been telling other people this is the demo they need to use for this sort of thing.
Absolutely.
But this is only the start of it.
That's right. Well, and one of the things they've talked about too is the fact that it's not just the NPU is not just the end-all be-all here. It's just because of the fact that a lot of it, for example, if you were on Stable Diffusion right now, you're tending to run on the GPU, and VRAM is actually one of the gating factors for it. So they showed off a demonstration of actually running Stable Diffusion 1.5 on 20 iterations, and then basically ran it against some different configurations. And there's really not really any easy answers to this. They showed it off like all CPU, and it took 43 seconds and it consumed 40 watts. They ran it on all GPU, 14 seconds, 14 and a half seconds, 37 watts. Then they did it with all of the NPU, which I assume to be the one that's in Meteor Lake, 20.7 seconds, 10 watts. So that was the most efficient one, but the most effective one in terms of actually getting it done was to combine the GPU and the NPU, which did it in 11.3 seconds and did it in 30 watts. So it did consume a little bit more power, but it got the job done faster. And I think some people, that's what they're going to care about.
I will highlight here, they didn't stretch the same workload over both. They separated the machining workload into two parts and did one on one on the other, but they did it simultaneously, I believe. And ultimately, there's a lot of conversation about, well, we have a CPU, a GPU, and now an NPU. Are there workloads that are going to stretch across both? I think stretch is the wrong term. They're going to be disaggregated among the set. So disaggregated tiles, disaggregated workload. And yeah.
It'll be interesting to see, though. I mean, you mentioned working with Microsoft, and I think that they're trying to get their OpenVINO libraries working with what Microsoft's doing, their APIs. I think there's more that we're not hearing here from behind the scenes work, because I'm not exactly sure what parts. I mean, this suggests basically that Windows is going to be accelerated by AI, but what parts of it? That's something we don't know as quite yet. So I think there's definitely more to that particular story.
Well, I mean, I'd love search to be accelerated by machine learning. Of course, everyone would, because everybody knows how search is playing right now. But they did also talk about a lot of the partners that are using. Maybe not OpenVINO, but a variety of different features to get access to the NPU. So Adobe was using one of the features. I'm sure we'll get a slide. There's a really nice slide showing some of these, how they're separated out. But of the 4 different kind of ways for most ML models in Windows to talk to the OS or talk to the hardware, they showed off different examples of each, and OpenVINO is one.
Now, can you help me a little bit? Because as I was talking with you before we started doing this, I think most people understand what makes for a good CPU. I mean, we're talking about core counts, we're talking about threads, clock speeds, power, and so forth, even caches when we're talking about Vcache with AMD. With the AI engine that they've got there, they're talking about 2 neural compute engines, each with their own MAC array, each with their own shaved DSP, tied to a shared scratchpad RAM. That doesn't mean a whole lot to me right now, and I think the question that we're going to be asking, in the future is what makes for good AI? I mean, what's going to be the things that people need to focus on? Is there anything that we can say about now about the direction Intel's heading and what we can look for in the future, do you think?
Unfortunately, the correct answer is no. The correct answer is no. I follow the AI hardware market, more sort of data center and edge type stuff. Yeah. And there are a lot of different architectures in play, whether that's kind of Google TPU systolic or something called a CGRA, or data flow architectures, or massive wafer scale architectures. There's a mix of approaches just because of how dynamic the machine learning industry is right now on the software side. Every week there are new models coming out. There are new ways for those models to be computed. Machine learning is all about having matrices and layers, and sometimes most of the time, the way you arrange those matrices or you arrange those layers or you do back propagation and feedback all changes. And so how do you develop an architecture that can do all of those at speed and efficiently? You could run everything on a CPU, but as you said with those numbers, you run everything on the CPU, it's going to run hot and it's going to run slow. So you need an energy efficient architecture that can approach most of these in a very power efficient way. So Intel's, essentially with the Movidius team have said that this architecture is kind of hitting the nail on the head that he thinks for the broad set of workloads currently in use on consumer platforms today. Will that be the same set of workloads for the consumer next year? We don't know, because it's such a fast-paced environment. So what they're trying to do is, while they're trying to have some acceleration with vectors and matrices and what have you, they still need to make it flexible enough. So in the computing industry, we often have this term called DSP, digital signal processor. And a digital signal processor is like an ultimate ASIC. It is geared towards one workload and it does really well.
Right.
Like a video decoder. If you know that all you're taking in is H.264 video, and that's the only workload you have, then you can pipeline those exact instructions to get the best efficiency out of your design. AI and machine learning is not there yet. So it's also a mix. What they're doing here specifically, I think that's worth highlighting, is that the NPU is technically a dual-core NPU. So they can either run one big workload across both, or 2 independent workloads concurrently.
Right.
Or if they're busy, you could arguably offload it to the GPU if you've compiled it that way. So all these little different things on how you design your machine learning engine you have to consider, but you had to consider those 2 years ago. So I think I'm very interested in what they're doing today about next year's product.
Yeah, I mean, I guess my question was more along the lines of, do you think that they're going to simply make it like a 4 neural compute engine? I mean, can we expect more parallelism in AI, or is that just okay?
Yeah. So with this neural engine, they have in the past kind of offered it on an M.2 card for embedded and industrial designs.
Right.
And I told MJ, Michelle, who we mentioned earlier, you need to make this M.2 card available for systems. Because if I've now got a motherboard with 4 M.2 slots, you've got a SSD in one, maybe in 2.
Right.
Maybe I want a high-powered NPU in another one of those. And if we have the right software to support that, then I can run machine learning on Intel hardware on any system with an M.2 slot. So the idea is that the architecture is scalable. It's I think internally they call this version 2.7 architecture.
Right. Yeah.
And the next generation is either going to be version 3 or version 4. So they are adding new features for future generation products. And yeah, I'm really hoping that they can scale it out beyond just simply being integrated into the chip, because I've seen demos with this thing running special features on OBS for streaming. Right? I'd love to be able to just have a system that doesn't necessarily have an NPU in the CPU, but just has an NPU on an add-in card that I can stick in and do all of that low power, hopefully low cost, and just offload it from the CPU. So
absolutely. Yeah, I think it's from what you're saying, and I think I would agree with you that they're trying to sort of just create a sort of rising tide lifts all boats, something fundamental, and as they start to figure out, hey, this is what people are using it for, then they start to specialize and accelerate those particular functions.
Yeah, they're trying to build an ecosystem around it, and I think having the hardware is stage 1, having the software support, having the software developers on board is stage 2, and they're going to be working through that. This isn't an overnight success, regardless of what's happened with either Apple or smartphone space. This is going to be a multi-year progression. Now, a cynic will say, well, wasn't that the same thing with AVX 512? The answer being yes, except that the desire for machine learning macroeconomically is so high right now, it was never that high for AVX 512. So,
speaking of AVX 512, as far as instruction acceleration is concerned, they talked a little bit about DP4A, which is a special AI instruction acceleration, which I think they first launched with ZLP and Tiger Lake, I suppose. Yeah. I'm guessing we're talking that seems to be. I'm not sure how big of a deal it is, but it seems to be something they're talking about.
Well, yeah, it's a GPU type instruction that was in XELP. XE, not
sure.
C.
Right, sorry.
I'll argue with that one as well. And this is part of their XE supersampling upscaling. Okay. Again, a dedicated instruction to help with machine learning, and they can use it in that context as well. It's just simplifying the throughput and increasing the efficiency and performance.
Perfect. Now, since we're still floating around the SoC tile, I did want to talk about something that we may have skipped over earlier, but I think it's important to mention, and that is what Intel's doing with Thread Director and its low power cores. There's a big change in Thread Director for this particular implementation, and the fact is that previously Intel would look to put new tasks, especially ones that demanded a little bit more, on the P-cores first. And now they're going exactly the opposite direction. So right now, according...
we'll see if we can show the slide here.
Yeah, if we can show the slide, we'll try to show the slide here. So right now, what Intel is trying to do is to take a new task and put it on the low voltage E-cores first, and to make sure those are always essentially in use, in saturated. And then if something else requires it, to bump it up to the regular voltage E-cores, and then finally the P-cores. And that's designed to save power, but it's also just a real change in their mindset from previous generations. Talk a little bit of that.
Yeah, so in the past, Intel has always parroted this race to sleep, right? Let's get work done. Right? Let's get the workload done, let's bring the CPU to sleep, and then let's save power that way. And with the desktop versions of Thread Director, you would get a workload, as you said, and put it on the P-core, on the high performance core. Right. Because if you're typing, if you're opening up the start menu, you want that to happen as quickly as possible.
Exactly.
So put it on the high performance part. This obviously consumes power, and if the core was idle before, you obviously have to ramp up speed as well. And so for a mobile platform at least, I'm not sure if that would change actually on the desktop platform.
Yeah,
we'll
right,
have to
good
wait
point.
and see. With this mobile platform, let's just put all the workload on the low power cores, and then if it meets the threshold for performance as determined internally by the CPU,
Right.
it will tell the operating system this is a good task to increase the priority. And as it increases the priority, it will be moved to the regular E cores, then to the P cores, and get high performance. Now, the question that immediately comes to mind when this happens is there an additional latency for this process?
Right, where they step up.
Yeah.
One to the next, yeah.
Because there's already some concern with Alder Lake and Raptor Lake that there is this latency differential when you just start a program due to the P's and the E cores, and now we've got LPE to E to P. They kind of answered that, and they said it shouldn't be noticeable. The idea being that they could switch tasks within a single frame. If you're trying to hit that 33 or 16 milliseconds to switch tasks, which should be plenty enough time to switch tasks.
Right.
But if it, I think the problem there is that if you have a lot of tasks starting on the E core, on the LPE core straight away, they're going to be fighting for resources before they're fighting to be promoted, and that could be a potential worry because we're in this method mindset now of programming of rather than just writing very linear code, let's make each new block of code a thread, independent thread. So these threads are going to be spawned within a task and then they're going to all start on the LPE cores. So I really hope Intel's done their background checking, their trace analysis, and they can fix this out because the ultimate step back would be to reverse that process through an update. If there was something in this design that I would want to point to and it's like, prove that works properly, it's Thread Director because most of us are enthusiasts, right? Right. We want performance, and then for those of us on the road, we want battery life. And on some level, I don't think you can have both.
Yeah, it sounded like a policy decision. Like they could go ahead and change the scheme for gaming, or they could change the scheme for whatever it might be. That suggested to me that yes, I mean we could see a reversal, like you suggested.
Yeah.
If something either went wrong or they just decided this was not the way to go.
Yeah, to be clear here, that there are two agents in play. There's a CPU itself, and there's the operating system.
Right.
Only the operating system can migrate a task to a high performance core. Technically the CPU could, but as part of the arrangement with the operating system, Intel specifically said we only provide hints.
Right. The OS knows what's going on.
Yeah, so the OS has to know what's going on. So the OS is essentially the arbiter. All the workload detection, so say you've got a streaming video decode or whatever, and you still need cores active for that.
Right.
It's the CPU can detect that and give a hint to the OS, but the OS actually has to do the change. This is why there's also a mix of responses, at least at the event we were, regarding Windows and Linux. Charlie, we know you're really into that. They did say work is being done on Linux and upstreaming. They just wouldn't provide a date.
That's right, exactly. Right. Okay, so we've talked about the CPU tile. We've talked about the SoC tile. I think we've hit most of the topics on the SoC tile. You want to talk about graphics?
Yeah, graphics.
Right. Okay. Go ahead.
I was going to say, Intel, very well known for their graphics hardware, bumping it up for this generation. They gave a 2x performance uplift gen on gen.
Yep, that's right.
And the question I had is, are you comparing that today, gen to gen, or launch to launch?
Right, exactly.
Because Intel's made such progression on drivers over the last year and a half, and they did say no, it's a today statement. Today previous gen to today this gen, they're expecting a doubling in performance. That's an increase in frequency. Because let's see if we can show that graph as well.
Right.
A really good increase in frequency, a reduction in voltage to reduce the power.
Yep.
So at the same power, 2x performance, and then I believe they were showing almost 2.5. The graph I think was very sneaky because I think the y-axis actually said frequency.
Might have, yep.
and it went up to like 2.5. So a 2.5 gigahertz Intel processor, I've been so used to seeing 1.1, 1.2 on this Tiger Lake thing. It's gonna be good to see 2.5 for the same power.
Ray tracing too?
Yep. Integrated ray tracing,
Yep.
though I think that's going to be a little bit hit and miss depending on how much ray tracing performance they can provide. It's so at the whim of the game developers themselves optimizing for it.
Yeah.
And I don't think they're going to be optimizing for mobile anytime soon. They're more likely to optimize for console.
That seems reasonable.
And the GPU in Meteor Lake is still not at the performance of a console. So.
I guess we can run down. We don't have. We can run down a few of the specs they showed. 8. You're pronouncing them Z cores, XE cores.
The official name is XE.
Thank you. I know. Yeah, spelling wise, that's true. Pronunciation is not something that I do offhand. 128 vector engines, 2 geometry pipelines, 8 samplers, 4 pixel backends, and 16 256-bit vector engines. DirectX 12 Ultimate optimized. They didn't show performance data, but they showed Forza Horizon 5 running at whatever resolution and whatever quality. I don't know.
I was sitting fairly near the front
did you
for
see
that, and it looked like at least 1080p.
It looked pretty
However, they didn't mention whether it was super sampled up or not.
Right. Yeah, I know.
It could have been a 540p upscaled to 4K. No, it wasn't. But I was happy in saying that was at least a 1080p medium, if not 1080p high. It is Forza.
Yeah, right, exactly.
It's not a Cyberpunk, and it's not a Starfield.
No,
but we'll
that's
see.
right. Didn't show off performance data, like I said, but they showed off some of the. Oh goodness, I've forgotten the exact term they used.
Synthetic tests.
Thank you. That's right. Yeah. So.
The tests we used to do back in the day when GPUs were really bad.
Good point. Yeah, that's right.
Things like vertex processing data, triangle fill data.
Yeah.
Somewhat arbitrary numbers, but still 2x to 6x. Again, we can show the graph on that.
Yep.
Always good to have synthetic data that is plus. However, the way games are built these days. It's going to be a mix of that. So I mean, I've got here higher maximum clock, low minimum voltage, roughly 2 times the frequency at the same voltage, and also a 20% power reduction when using machine learning workloads on the GPU.
Yep. A couple of things that I liked: HK60 HDR, 4x 4K 60 HDR. So we're talking about 4 driving 4 monitors. I have actually 4 4K monitors at home because I use it I test Thunderbolt docks, so it'll be interesting to see what happens with that. 1080p 360, 1440p 360. So again, that's some nice numbers for gamers. Let's see what.
Yeah, you can run your Counter Strike at 360 FPS off your laptop.
That's right. Yeah, exactly. So that's always a plus. I mean, I have that way my son can stick with his laptop and not have to bug me for a desktop, which is hopefully good. What else we got here? I mean, there's a couple of other numbers we can throw at you. The ray tracing was 2.64 times what was did in Raptor Lake in the in Classroom and Blender. A couple of other things with the support for various codecs. I'm not sure if they matter or not.
The super sampling. They didn't give a performance metric, though they did give a power metric, and they're saving about 30% power per frame on the super sampling. I assume there's also a new algorithm in there involved, not only with the efficiency of the architecture. And I think an important thing here is one of the new features they're adding is this sort of endurance gaming arc control feature. So you're used to, there are features in other GPU softwares where you can fix the frame rate, whether it's 120 or 60, and typically you do that in a device like this because you don't want to use more power than you have to, and you don't want to increase the temperature as much as you have to. So as part of the endurance gaming arc control, they will enable a max battery, an advanced, a balanced, or a relaxed. So that's 30 FPS for max battery, or relaxed at 60. And the whole point here is that the number that they gave, pinch of salt and all that, Rocket League can run at the is it the 30 FPS mode max battery at 1 watt.
I think that's right.
So you can play Rocket League with a 1 watt GPU.
Yeah, it's pretty impressive.
We're going to have to measure that. Rocket League isn't the most demanding of games. And we'd have to see what happens in a big multiplayer workload for that.
As far as power too, I think when they were talking about, one of the things they were talking about was the sort of the new enhancements in panel self-refresh. So if there's a repeated frame, they just actually don't even wake the core. They just go ahead and
Yep.
yeah, right. So they do some frame queuing as well as there too. So some smart decisions, I guess.
So that's video decode. What we're talking about here is, rather than decode a frame, show it, decode a frame, show it. It used to be you'd decode a frame, and then even if it wasn't ready to show that frame, you'd start decoding the next frame, and then you'd have a little bit of idle time. Now they can decode 16 frames, and they go to idle for the rest of until it's time to decode the next one, frame 17. So ultimately, you can have an idle period of over half a second with 24 FPS content. Which the film fanatics will love.
Right.
But it also means when you're watching video on an airplane,
Yeah.
it extends the battery life a lot better. So
Also, too, I don't know if this is important to mention, but the XC LPG has its own tile. The XC integrated, or the median display lives in the SoC tile, so it's separate, and then the display lives in the I/O tile. So again, they're separating these things out to try to minimize power consumption if they can.
yeah, it's because the GPU tile is pretty big, and video decode and encode is kind of a different process altogether. It's still graphics, but it's a different process. There's no need to wake up the GPU tile.
Yep, exactly.
And that's what that's designed for.
All right, we've gone through a lot. Anything else with Media Lake?
So in terms of a little bit of the I/O,
Photos, maybe, I don't know. Sure.
yeah, a little bit of the I/O. So the I/O tile is the little one in the corner.
Yeah, the extra, the
that,
appendix.
Yeah, that simply holds Thunderbolt and PCIe.
Right.
It looks like there'll be different variations of that depending on whatever the SKU
That's
is.
true, right? Yeah. I mean, we talked about PCIe Gen 5, right?
Yeah,
but
yeah.
Thunderbolt 4 is what I heard. Yep,
Yep.
exactly. Yeah. So not the 80 gig stuff, unfortunately, but that could come in the future, I guess, with a different I/O tile. So.
Yeah, it's should be fun. Well, this is the whole point of this disaggregated system, right? If they build a different function, different feature like Thunderbolt 5, or they need to fix something in a DisplayPort engine, for example, they can just swap out tiles.
That's it.
And obviously you still have to send your product in to get it changed. But now, I think what we'll see from this point on is that gen-on-gen advancements, you may not see everything in the chip updating. So you may get better CPUs one gen, you may get a better memory interface the next gen. I mean, I don't think that this kind of configuration with the 5 tiles will ultimately be a final configuration. It's good for now. I really want them to change some things from a business perspective. But it does mean that they can do that and be effective, and obviously different SKU out. I mean, we said right in this video, this is the H682, right? There could be a different one coming along later.
I'll tell you one thing, as far as actually putting this stuff in print and like listing the various specifications of it, I mean, right now, it takes up, I don't know, better part of 30 words just to describe that particular chip, and as they start putting in different tiles, it's going to even make it more complex. I mean, it's just going to be, it's just a challenge.
I do wonder for how many generations we'll have to speak about tiles. Until it becomes a bit more common knowledge. Not anytime soon, especially because they'll be doing so many enhancements generation on generation to drive down the power, do the better integration, packaging, and all that fun stuff. What we're waiting on from that point is actual performance data and product, and then lead partner devices. Exactly when it will hit the market, Intel has been kind of consistent in saying by end of year.
Right.
Though we're not sure in what volume. I think CES will be a big launch for that. So don't count on getting one before Christmas, but come Q1 we should start seeing a lot more enter the market, and I think that's going to be pretty important.
So that was Meteor Lake. We're now going to shift gears a little bit and talk about what Intel showed us in Penang and Kulim. Again, assembly is part of the manufacturing process, but not one that normally gets talked about. Malaysia is also the first country that Intel expanded to more than 50 years ago. So it's important to talk. It's important for both the company as well as employees to sort of show off what it can do.
I think we should talk about the process. So
Yeah, absolutely.
Right now, everybody I think listening should be familiar with. You get a silicon wafer. You print.
That's it.
You print a design on it, and then that's what the fab gives you, right? Now, what do you do with it?
Right.
Right. So, part of it is die sort, die prep. So you actually need to cut the wafer into bits,
That's it.
and then pull all the different dies out. Then you need to test to see which ones are good, either electrically or functionally.
Right.
And then you actually need to package them. So those 3 steps are just as important as the manufacturing the chip itself, because without them, nothing happens. Obviously, after you assemble them, then you have to test them again. So
That's right.
It's die sort, die prep. Testing, assembly, test again.
That's it.
And every CPU that goes through Intel does this. I think the site said that they've been through 500 million computer chips since 2020.
I think so. Yeah.
Yeah,
That's
so
right.
500 million in 3 years, just for this, just for Intel in Penang and Kulim combined.
Right.
Insane amount of volume, and they shut it down for a couple of days for us to go see.
Exactly.
Financial people don't ask how much it cost.
I mean, just to give you a bit of a description about what the process was like. I mean, we took a bus out to Kulim. It's very tropical, sort of reminded me a lot of Hawaii. Lots of palm trees, lots of and so forth. Just sort of a very lush, wet environment. And then all of a sudden, you have these really advanced facilities, these advanced fabs just kind of sprouting from the grass area. Now, this is a high security place, so we did not get to take, not kick cameras in. We couldn't take, even in some cases, we couldn't even take pen and paper in. So some of this is being done by memory, and it's not going to necessarily be, I mean, from my standpoint, not entirely accurate at some point. Ian's better than I am.
They almost threatened to take our eyeballs. But,
That's right, yeah,
we managed to convince them to keep. Let's keep those. What amused me is we had to drive to one car park in a big coach,
Right, yes,
and then go to
yes,
smaller
yes,
buses because
exactly.
because the coach wouldn't go through the roads.
Right, yes.
I'm like, hang on, this is a multi-billion-dollar facility.
And they couldn't even get the roads right.
And we're having to go down the road in what is the equivalent of a rascal van.
That's what it was.
Yeah.
Exactly. I sat in the seat for pregnant mothers because it had like leg room. Yeah, it's great. Yeah. So
I don't think pregnant mothers are allowed in the
I wouldn't
fabs.
think so. Yeah, exactly. So, anyways, though, yeah. So we had to, and then we, of course, for some of the places, we had to get in bunny suits. So you've been in a bunny suit before.
If you go onto my channel Tech Potato, you'll find a video on how to put on a bunny suit.
Oh, well, there you go.
That was at Intel Oregon.
Oh,
so
perfect. Well, then, yeah, you have more experience than I do. So we had to go ahead and sort of submit at least I had to go ahead and submit my shirt size and so forth, pant size. So we had in some places we had more.
PPE.
Thank you. That's
More
right. More
P-
PPE than others.
They
Yes.
actually had our suits with our own name on,
Right.
as in a vacuum sealed
Yes.
bag. That's not every facility I've been in. Typically, you normally just pick one off the shelf, but they had this tour down to a T.
There was so much manpower devoted to assisting us getting our bunny suits off, They had people that were, normally you have like traffic cones. They had individual people set up so we wouldn't go walking elsewhere. I mean, and it wasn't just one or two. I mean, it was like 8. I mean, they had a lot of people there.
Every time you walk down a corridor,
Right.
and there were potential left, rights, there was somebody there on every one.
Absolutely, yes. They want to
yeah.
make sure that we're not going to go wandering off. So.
Yeah. Maybe me more than Mark.
Yes, you didn't. Did you actually get a wafer to chew on? I don't think you did you?
Sorry?
Did you get a wafer to chew on?
During our tour, this is perhaps a little bit of an aside,
Yeah.
one person on our tour did drop a wafer.
They actually dropped one?
Yeah.
Really?
One of the influencers' cameramen, I believe, this is what I've been told, dropped one during a photo shoot.
Wow.
That as part of we said no cameras, and that was true. They did have on-site photographers,
Right.
so they did set up a place for us to kind of hold some chips and some wafers. and obviously some of the influencers were invited, and they bring obviously their audio-visual guy, and they were trying to direct them to make sure, and one got dropped.
Did it shatter?
Yes.
Nice.
Test wafer.
Oh, right. Okay.
So not a no. In these toys, they never let us handle production silicon on purpose because it's really expensive if it does break. But breakages happen, and that happened.
So one of the things that I was really kind of impressed with Kulim and the dies. So the dies come out in wafers, and you've got to get them off the wafer, and they're encased in fabric, or sorry, not fabric, mylar. Plastic, sorry. And so they get sawed, but the saw doesn't go through the plastic. And then there's a laser cutting process as well. That I still don't understand quite how that works.
So the saw does go through the plastic.
It doesn't, because they didn't say this. We asked them. They said no, it doesn't.
It doesn't go through the back end of the plastic.
Okay.
So the idea is you take this wafer and you put it inside like a mylar clasp.
That's right.
It's like it's a metal ring with two sheets of. They say mylar. It's probably some variant of therein, and they put it in, and then you literally use a mechanical diamond tipped saw.
Right. Yep.
And it cuts the dies into what they call the scribe lines. So if you ever do any die wafer calculations, you always have to talk about scribe lines, and that's literally the width of the blade, 0.2 micron, 200 nanometer wide blades, because you can't laser through silicon, at least not like that yet, and then because it's trapped in this it was trapped in this mylar sheath to begin with, because the scribe lines are so fine, the glue from the mylar still holds everything together.
Okay. Right.
And then they have to wash off the mylar from the top, so they dissolve it in a fluid as well. So it's still stuck on the bottom with the mylar, and then obviously that wafer has to come out of the machine, and it goes into another machine that can pick individual dies up and put it on a tray.
Yep, that's right. And then from there, help me out here, 'cause it's all a little foggy.
I mean, to be honest, when I visited this facility, I actually visited it backwards.
Yeah.
As well.
Right.
Yeah.
Right.
Yeah.
Okay, that's true. Yeah. It was an odd process.
The other group went the right way. We went the wrong way. So we just drew the short straw.
Oh, well, okay. All right. And then from there, does it go into the reel, or does it go actually? Does it stay in the tray? I think it stays in the tray, doesn't it?
It stays in the tray.
Right.
Yeah. So you have to do some small amount of electrical testing.
Right.
Right. So this is where it's just making sure that the dies work, that you haven't had any defects, electrical defects, because when you're printing such small circuits, you have to make sure you don't have any shorts. So it's not necessarily a functional test; it's an electrical test. But you remember, it goes into those big machines with 20 different testing machines that are like 1.5 stories high.
Yep.
And in order to move these all about, there's this machine that glides on a thing of air. You remember what I'm talking about?
Of course, absolutely.
Which is a slightly different room. So this is going into making sure that the die are what's called known good die. So it's die sort, die prep, right? So this is the sorting phase.
That's right.
It's this isn't necessarily where they do the binning for the different SKUs, but they could determine, say, whether 6 cores are active, 4 cores are active, 2 cores are active. Because if there's an electrical short, it's not. And it's at this time they kick out all the bad dies, right? So all the ones that definitely don't work, they get thrown in for recycling.
Now this was, I want to stop here because this had two of the cooler things that I thought we had. So we had, first of all, you mentioned, of course, these things they're moved on these sort modules, which are apparently like 1,000 pounds.
Yep.
But
expensive.
But they're moved on air. I mean, that's the thing. So it's like this. It's like
air hockey.
Exactly. It's like an air hockey table that would move 1,000 pounds, and I have no idea how that works. Because I mean, these things were massive. I mean, these things were about the size of a storage unit or something.
So there were wheels underneath.
I didn't see any wheels. Did you see wheels?
There are wheels.
Okay, well, they had to be wheels. Because,
Yeah,
I mean,
the-
how would they work without it? Because, I mean, there's no way you could push
so
1,000 pounds of pressure up.
You have this such big machine, you obviously got some suspension in there,
Okay.
pushing all the way heavily down the suspension. Now, how do you reduce the pressure on the suspension so you actually get mobility?
Okay, that's a
you
little bit
fire air jets down
See, we must
onto
have,
the floor.
our tour just didn't go into this because it was like this like abracadabra, like waving it on the air pressure or something about something. They mentioned they did not mention.
They
wheels
did mention it on
ours.
ours. I just assumed.
Oh, I don't know.
I mean, that's just mechanics.
I would think so.
Yeah.
exactly. I mean, otherwise the air pressure coming out of the sides of that thing would be immense. Yeah. So all right. So anyways,
It wasn't as loud as it should have been.
right.
If they had no wheels.
Exactly. That's right. So they had those things going on, but they also had the little automated robots essentially.
Oh yeah.
Right.
So you've been in the Israel fab.
No, I have not.
Oh no! You didn't
didn't
come
go.
last year.
No,
So this is your first time in a bunny suit.
Yeah.
Oh wow.
Yeah.
So this is like my 5th time in a bunny suit. So perhaps I can offer assistance here.
Sure.
The big manufacturing facilities, whether you're talking about Intel Oregon, Intel Israel, or like IBM or Global Foundries Malta, they all have automated. They call it the like the automated superhighway or something.
Right. Yeah. There was a name for it.
I think it was ASH. I can't remember what A stands for right this minute. But the idea is that you have these machines that pick up wafers in batches of 25 in this like black acrylic box called a FOUP. That's a front opening unified pod. And then that FOUP gets shipped along all the way through to wherever you need in the fab. So that's a fab. That's where you actually make the design on the chips. Because this is not that. This is die sort, die prep, assembly, and test. The machines are actually on the floor. So it's just little machines that have, they're battery powered, they're automated, they know where they need to go. There are sensors everywhere telling where every machine is. There's a person on the factory floor, an admin who can remote into any of these systems. If one gets stuck or one happens to run out of battery.
4 hours, I think it was. Or something
Yeah. Each machine had only 4 hours of battery, but they'd go back in. They'd go like a Roomba, basically.
exactly
Go
what
plug
it
it
was.
back in,
That's it.
half an hour recharge, then back on it. And the idea was to simply. Sometimes this group of wafers needs to be moved from this machine to the next, or from storage to this machine, from there to there. And they said each one of these point-to-point activities take about a couple of minutes. And
Yeah, they had little lanes that go in like that.
yeah, and they would actually identify people and move around people.
That's right. Yep.
Because I know in our group, one of them got stuck because he kept trying to go by. But yeah, no, they're saying that this saves so much manpower, hundreds of kilometers per day, per machine. When in reality you're thinking these things are really heavy because you shouldn't be able to tip them over, and they require so much power to get going. But ultimately, if you look at the cost in terms of yield, that would the yield loss you'd get from just manual handling, it's worth it. And
The thing that struck me about it was the fact that every time it moved, it played a little tune just to alert people, and it was like your cell phone your ringtone going off. But it was ringtone. It wasn't just going off. It was just playing over and over and over. And these guys
and
had
8 of them.
These guys had to have had that stuff in their dreams. I mean, I can't imagine. It would just drive me insane to hear that thing over and over and over again.
Well, you also had the loud, the airflow off the room.
That's true.
Being,
That was white
being
noise.
really loud.
Yeah, that was.
But
white
the point
noise.
is, at least in one of the other facilities, if one of the machines has an issue, it plays a different tune,
Oh.
like Jingle Bells.
Oh. Well, that's useful.
Yeah. So
you
the
can
ones
tell
so
the
the ones
difference.
where I've seen them going overhead,
Right.
they didn't play a tune unless something was wrong.
Okay. All right.
But yeah, it's there was a noise. I thought initially it was the radio for the employees, and they were listening to local music. It turns out that's not local music. That's just me.
All right, so maybe we can shift gears to the Penangs, which did a little bit. This was the assembly and test. So just looking at just my notes.
Sorry, one thing.
Sure.
Of
course, no, absolutely.
One other thing in Kulim was the what they call the SIMS module.
Oh, right. Yes,
So-
exactly.
so,
That's a good point to talk about that.
One of the points that with a CPU, you need to test how it works. How do you test how it works? You build a test machine.
That's right.
How do you test that the test machine works? You build a test machine.
That's true. Yep.
It's turtles all the way down.
Yep. Exactly.
So in order to build the machines that test the chips, in order for validity, they have what's called the SIMS I'm not sure what SIMS stands for. We'll show it up on the screen. But this is where they actually design massive integrated systems that you can put the chips in to do the testing. It's imagine like massive custom motherboards with FPGAs and power electronics and memory. And this machine does this one thing, this machine does this another. And maybe if you spot an issue, somebody will go up to the machine, actually have to rotate it round with powered metrics and probe it in. And people say, what's the FPGA market for? And it's actually for doing a lot of this testing. Because test machines, making sure it all works, and then actually, because Intel does so much custom testing for their custom chips, they have to build their own custom test machines, and then custom test machine. Because everything is so bespoke for Intel at this level, they have to create it themselves,
Right.
and that requires having dedicated facilities just to test
Their own testers.
And it's insane. You'll see like 48-layer PCBs of just something that's designed to test multiple CPUs on one rig, and you'll have this microfine tipped probes in order to make electrical connections to make sure that some of this tests work. And it's really expensive.
And
stuff.
it wasn't really automated either. I mean, they had just ordinary, women just in there, like like a motherboard, building a motherboard 10 years ago. They would just, be in there fixing particular components to the boards, and just, doing their thing.
Because these machines are so bespoke and they only need like 50 to 100 of them, it's not a production facility.
It was not. Yep.
It's a one by one by one by one. But then they have to do this for every single product.
That's it. Yep.
And obviously, you try and find some synergies. Like this is a testing rig, but you have a different head on it depending on which CPU you're testing. And they were showing some of the products that they've been testing there over the years, going all the way back through, pre-Skylake and some of the custom chips like Sky Meadow that they've done, and then also the FPGAs like Falcon Mesa. All these are Intel code names because they decided to use code names and not product names. But yeah, no, there's some stuff going way back, and just so much dedicated hardware just for this one. And I found that pretty. I could have spent another few hours there just trying to learn a lot of the process. So, but they all had their scripts that they had to adhere to.
Yes, that's right, exactly. Yeah, well, for me, honestly, the stuff, the Dysort and operation was more interesting, as well as the Penang facility, which basically, I guess, was sort of the second half of that process. I mean, all of these dies simply get shipped to what they call PGAT. Which assembles and tests chips, and you probably know the process better than I do. But as far as what they told us, as far as the 6 key stages, where there were chip attach, there were epoxy and lid attach for the assembly, and then it was basically burn-in test, and then the platform validation, which was all important parts of the process, and basically things that we got to see too. So it was pretty cool.
Yeah, it's so one of the chips that they assemble in that facility is Ponte Vecchio.
That's right. Yeah.
So Ponte Vecchio is 47 tiles.
Enormously complex.
So you have to be able to test those tiles individually, then package them, and then test them. Not necessarily in a 47, but maybe you've put 3 together, and you need to test those.
Right.
Just so you have consistently known good die until you build your product with fully, so everything fully works when you put it together.
Right.
But so. Not only do you have your assembly, you've got your physical assembly metrology process. So this is things of using ultrasound in water to determine if the top of the CPU is actually flat. And then you've got assembly, which is attaching the silicon to the organic substrate, the green thing that your CPU is in.
That's it.
Making sure you have good connection, you have epoxy underfill underneath. That's like the little glue that you sometimes see. And then you have either thermal paste or that the solder mask that they put on the high performance processors. And then you see trays and trays and trays and trays of heat sinks.
Yep, that's it.
Just the metal heat sinks, and then they have to stick them on. They have to put the glue in. If you've ever delidded your CPU and wondered why is it really hard to get off,
that's right.
It's because some of this glue. but to be honest, you have to think about economics of these things. People in the past have criticized Intel for skimping on thermal paste in between the CPU. and or it's not as good as the best you can get, and you can save 10 degrees by using your own. But at the scale that Intel's doing this, again, 500 million in 3-4 years, if you save 1/10 of a cent in thermal paste per chip,
Right.
that actually makes a lot of savings. And you have to decide, as a company as big as Intel, is it worth it to make the savings, or is it worth it for the performance delta? If you want the performance delta, then you have to shout at Intel more.
So
right?
there were two things that actually struck me during this process. I don't know. So first of all, when they were applying the epoxy, I was assumed that everything would be very organized. It would be very. It would come out in a very neat layer. It wasn't like that. It was like there was excess, and they just didn't seem to even care so much about it. And that was one thing that struck me.
Well, when you put the silicon on the substrate, right? You've got the little solder balls essentially connecting, and these are really tiny. And you put in the epoxy in between such that it fills the gap. It removes all the air.
Exactly.
So you can reduce any potential for electrical shorts or electrical disconnects. And they put the epoxy along the side, and the rest is done by capillary action. It's the natural force based on the surface tension of the epoxy. And as a result, they typically only epoxy one or two sides of a die, and they expect it to go all the way to the end. Maybe they might do a little bit at the end just to make sure that that's filled in. And they overfill it because they need to ensure 100% coverage with the epoxy. And obviously, they've done this for so long. They've got models about how, just by random variation, how often does the epoxy actually go to the rest of the edge of the chip.
Right.
And they've got to cover 100% of chips, right? Because you don't want to leave any yield on the table for what is a relatively easy part of the process.
Totally grok that. It just seemed a little sloppy. I was just like, wow. I just for a company that's designed to to do this down to sub-micron efficiencies, it just goes like wow, just kind of smeared it there. But all right, that's fine. The other thing, I don't know, one of the questions that was asked during the lid attach, the heat spreader was, so how does it feel if there's entire businesses set up to actually remove those lids? And she felt like the woman there was just like, well, it makes us feel kind of sad in a way.
Well, so Mark and I were in slightly different groups going around the tour.
Right.
And that came up. I said, there's a guy who's made a business of
That's the same question.
of actually creating a physical device to remove these lids perfectly every time. And it's like, why do they want to do that? And it's like, well, they want another 10 degrees on their CPU cooler. And it's like, oh, obviously the people we're speaking to, it's not their decision to use a cheaper version of the paste or whatever.
Right.
But yeah, it's. To be honest, part of the feedback I got from some of this, because we also had some of the engineers for the product on the tour as well, they hadn't seen some of this stuff.
Really?
So it was giving more of. It was not only giving the packaging experts a deeper insight into Meteor Lake and the products, but also the Meteor Lake people just more insight into how the product is put together.
That's interesting. Should we talk a little bit about like the final part of the process, which is the performance validation?
This
was kind of neat.
This is Intel doing its internal review of a processor.
Right. Yeah. Exactly.
It's taking our jobs.
Yeah. Right. But it was interesting because it was essentially a lab with workbenches like you would see both in PC World or someplace else, just rows and rows of hardware, rows and rows of equipment. They had different stations, so we kind of got sort of a hopscotch through the whole process, I guess.
They limited to one area of the room that they cornered off
Yeah.
with specific people with specific systems on display.
Exactly, with people blocking it off, although they had some ropes and places and so forth. So I don't know if we want to talk too much about it, but they had all sorts of different validation platforms. I think the thing that struck me was the fact that they had reference validation platforms which were individually tailored towards specific customers. Like, for example, I guess if there was a Dell that had a specific product they wanted to go ahead, they would go try to mimic that to some extent in the lab.
Well, so the test and validation, you have electrical, feature, and performance. So if you do have an OEM partner who's designing a motherboard for a laptop, for example, you need to make sure that all of those things work in that form factor. So I think that's a lot of what we saw, because in a laptop you may have integrated DRAM, you may have a SODIMM, and that's going to be slightly different versus having DDR modules on board, and all the Wi-Fi, maybe that's directly attached, maybe that's a PCIe card, and so you still need to know that 3D Mark works when you have a different Wi-Fi solution. It's that sort of thing. I mean, all this testing, I will say, all the software was automated, right? You could see the interfaces that they designed internally.
Yep, that's right.
Whether that was things like running PC Mark or 3D Mark, they were a big proponent of UL inside. That's why it has the UL mark, obviously. But they were also doing functional tests such as individual CPU instructions, GPU synthetics. That was a big part of that.
Yep. Even using some AI occasionally too.
Yeah. Because it's a new workload. You have to test the new NPU in Meteor Lake. So on top, all the tests were automated. They also had stations where the hardware was automated. So you'd have essentially a CPU socket, and they'd put one CPU in, close it, do all the tests, then they'd get the okay to change the CPU, lift up the module, pick up, take out the next CPU, put it in the tray, get the next CPU. So if you want it from a reviewer's perspective, that would be ideal.
I know, right?
Because then I could just line up the 25 CPUs I want to do in the next review, and just press play, and it would go through all of them. And then you realize the software crashes after 8, and actually it's been wrong since number 3. That's the danger of automation. But as a massive company, Intel can't do that at scale without automation. And it was prevalent throughout the whole, aside from the test equipment manufacturing, there is just so much automation everywhere. You just can't get away from it.
And they run different tests at different temperatures too, the hot tests, cold tests and everything too. It makes sense.
Making sure the CPU runs in a 85 degrees Celsius environment.
Different levels of voltage, the whole works.
But also in customer platforms, making sure they run at 85 degrees. Celsius and what have you. So.
Geez, you walk outside, you realize the hot tests aren't necessarily that out of whack, I guess.
Yeah, well, they're not building testing facilities in Oslo, are they?
No, they're not, unfortunately. Yeah, that's right. So.
It's. The whole site in Malaysia, they said they've invested 15 million since it started, and the next expansion is 7 billion over 10 years. Where they're increasing another 700,000 square foot space for all of this to what total 2.1 million square feet or so.
I think it was. Yep.
Yeah, and I have to remind people, if you listen to Intel about their manufacturing expansion in Germany, this is 2.5 times the size of that, right? It's as Intel moves into foundry services, they're going to need more space.
Yeah, absolutely. All right, I think that's it. That was the Intel Tech Tour.
Malaysia in a nutshell.
Yeah, exactly.
So this is Intel's second Tech Tour.
Yeah.
Expect number 3. Yeah, should be fun. Intel 4 should be fully up and ramped. The question is, well, you'll get to see a fab for the first time, right?
Yeah, that's true.
So it should be fun, and we might even be seeing the start of Intel 3 there as well.
Yep. Good drinking opportunities.
Yes, we may have seen Intel 3 already in the.
It's possible. It's hard to say. Yeah, there was a lot that was out that I don't know if some people picked up on and some people didn't.
It's if you look slightly around the corner, that you shouldn't have been necessarily.
Yeah, that's it.
There are a few things like that.
Okay, well then I guess we'll go ahead and let it wrap up. So I'm Mark Hockman with PC World. This is Dr. Ian Cutress. Check it out. Keep it tuned to PCWorld.com's YouTube channel for more. Check out Tech Potato for more of Ian's awesome videos. And thanks for joining us.